Alright, now we're going to start today's lesson about functions and their inverses. It's a pretty simple lesson, kind of pairs up with yesterday being a simple lesson. I think two inverse functions you're already very familiar with are in the form of formulas. You guys know the formula, this formula and this formula. What are those formulas right there, guys?
Fahrenheit and Celsius.
Fahrenheit and Celsius, okay? So the first formula you would use if you know Celsius and you're looking for Fahrenheit. The second one is the opposite of that. You know Fahrenheit and you're looking for Celsius. So when we think of these, they're somewhat inverses of each other. They undo each other. Now, when we're talking about pure mathematical functions, we denote inverses with this little exponent of the -1. But it is not like this. It's not like that. It doesn't mean reciprocal. This -1 is in a different position and it has to do with functions. Alright, so f inverse of x. Or you could read it the inverse of f of x. Either way. But this is the symbol that lets us know we're dealing with inverses. So how do you find inverses? Very, very simple. It's a three-step approach. Step 1, switch your x and y. Step 2, solve for your new y. And step 3, rewrite using inverse notation. That's it. Very, very simple. Joseph.
What's the numerical significance for like the plus 32 and like 9/5 when you're converting Fahrenheit to Celsius? Did they just pick random numbers?
No, it's actually the relationship. So if we were to take measurements of temperatures in both Fahrenheit and Celsius and we were to do a linear regression, easy for me to say, that is the equation that would be established given the relationship between those two variables.
I do, you're honey, because you won't be lying. I do. So, you're gonna dig a hole deeper.
Alright, so here we go. F of x means y. So if I switch my x and y, that becomes x, this becomes y. And then I solve for y. So I'm going to move the 6 over. It becomes positive. I'm going to divide by 2. And I'm done. So this is the inverse of f. So let's state it. F inverse of x. So we're going to use that inverse notation. Now, of course, I could also write this as this because those are equivalent expressions. And they're equivalent inverse functions. Did you follow me?
I lost you after you did x plus 6.
All right, so I moved the 6 over. And then I divided by the 2.
Okay.
So I can either write it as a big divide by 2, or I can divide each term by 2. So x divided by 2 is 1/2 x,
Okay.
and 6 divided by 2 is 3.
All right. Good.
So you could write it either way,
I'm not.
an either or situation.
Either or.
Okay, now, what I've done here is I've graphed. The blue one is f of x, okay? So the blue graph is f of x. It's obviously a very simple line. It has a y-intercept at -6. The slope is positive 2, of 2 over 1, all the way through. Draw your line. Okay, the red one represents the inverse of f of x. So if we notice it has a y-intercept at 3, it's up 1 over 2. There's my points. Now, the cool thing about this is, do you notice when I draw in the line y equals x, this red and the blue line are perfect reflections across that line? Yeah, they are. Let's think about why. Now, when you studied all those transformations in Algebra 1, one of them was a reflection over y equals x. And what happened when we reflected over y equals x? It switched the positions of the x and y. What did we do up here? We switched the x and y. And if we notice, if we pick any point on the original function f of x, 3, 0, we switch that point, look. There's its reflected point on the other side of the y equals x line. Okay? Now, with us switching the x and y, that also affects the domain and range, doesn't it?
Yes.
Now, in a line situation, it makes no difference because the domain of a line is from negative infinity to positive infinity, and the range of a line is from negative infinity to positive infinity unless that line happens to not be a function. What's the only line that's not a function? Line.
Oh.
What kind of line is not a function?
Vertical line.
Vertical line.
Oh.
Okay.
The-
So as long as it's not a vertical line, we got a function. So since the domains and ranges are exactly the same, when we switch them, we can't tell any difference. So now, here's our one new vocabulary. We don't do much vocabulary in math, but we got one right here. A function is said to be one-to-one. That's a special label. It's a special kind of function. It is one-to-one if the function and its inverse are both functions. Now, obviously, this function we just took a look at, f of x, is a function. Because the blue line passes the vertical line test, and the red line passes the vertical line test. So, that function could be called one-to-one. Because the function and its inverse are both functions. Alright, now, if you only had the graph of the original function, so let's say I only had the blue line, we could use that original function f of x and do the horizontal line test to determine if its inverse is a function. Now, does that make sense? Vertical line test is x equals. Horizontal line is y equals. So inverse switches x and y. So to tell if the inverse is a function, we would use horizontal line test. So if I give you a graph and it passes the vertical line test, the graph is a function. If it passes the horizontal line test, its inverse is a function. And if they're both the function and its inverse are functions, we could call it one-to-one. Okay, you ready? All right, so let's check out some. Now, look at this one. This is a squiggly, and it passes the vertical line test, so yes, it is a function. But would the inverse of this squiggly be a function?
No.
No. So would it be one-to-one?
No.
No. Okay, number 2. Is this a function?
Yeah.
Yes. Is its inverse a function? That wasn't really horizontal. Let me try again.
Because
But anyway.
it goes to-
No.
Okay.
So is it one-to-one? All right.
Yes. that is.
Yes.
And it's yes again.
And it's yes
And
again.
it's yes.
So it's yes.
All three yeses.
Okay, we are going to have to do a little bit of restricting on the domain to keep that inverse a function, and we'll see that in just a second.
We done that yesterday.
Yeah, we sure did.
I'm trying to think about
We sure did. We talked about it.
on the graph.
Okay, so
You try.
example 2 is a you try, but it's the Friday before winter break, so I'm going to try it. All right, so step 1, what do I do?
You have
You switch back to Y.
Yeah.
Switch X and Y's. All right, as long as you guys can tell me what to do, I know you can do it. Now what do I do?
Solve for Y.
How do I do that?
Multiply by 3.
Multiply by 3. I like it.
And then subtract 5.
And then subtract 5. And then last step, throw in a little inverse notation.
Oh, you just try.
Yep. Multiply by 3, that
Oh, yeah,
goes
yeah,
away.
yeah.
Subtract 5.
Julian, shut up. Oh boy, I realized my mistake. As soon as I said the question, I was like,
All right.
Stop talking. Okay.
Number 3. Our function is a little more complicated. It's one of the square roots we looked at yesterday. I've already graphed it. It's this little function down here on the bottom, the original. All right, so if we go to find its inverse, this becomes x, this becomes y, and there's a little more work to get y by itself. Okay, so y is grouped up under with this 1 under the radical. So we got to get rid of all the extras. So we got to move the -3 and the 2. What goes first?
Square. No.
Three.
Add
The
three.
3. Add 3. And then what do we do?
Square.
Divide by two.
Divide by 2. Alright, so now we're left with just the radical part. And now we square it. You are right.
Say square to square.
Whatever you do to one side of a function, an equation you must do to the other. So this is x plus 3 over 2 squared. Or, could I write it like this? 1/4 times x plus 3 squared. Think about it.
Oh, yeah, because you square the 2 and then
Okay, so those two are the same, really. Yeah.
If it was a 3 on bump, it was 9.
And then over here we have y minus 1. So either way, I could write it. So if I stuck with the bottom, and inverse notation. Okay, so this is a parabola, which we know a parabola looks like that when it's like this and positive. 2. So what do we do?
Grab and give up.
If we look at this one, does it have 2 sides?
Yes.
No, it just has that one. Okay, we got to go back to what we know. The domain of this original one went from 1 to infinity, and the range of the original went from -3 to infinity. When I switch the x and y's, what will be the domain of this new function? The range of this function becomes the domain of this one. Because what does range represent? All possible y values. So, since range represents all possible y values in the original function, that becomes the domain of the inverse. Because we switch the x and y. And domain represents all possible x values. Now, if I restricted the domain from just -3 to infinity, do you see it just gives me the right side of the parabola? And does it look like it's a nice little reflection over y equals x? Yes. Okay, so sometimes we have to restrict the domain because the actual domain of this function would be from -infinity to +infinity, but we don't get all of it if it's the inverse of g of x. We only get the part that represented the y values in the original function. So, if there is a restricted domain, you must state it. If there's not, if it's still -infinity to +infinity, if there's no restricted domain, you don't have to state it. But if there is one, state it. Okay, last thing. Going back to the first example, we found, I gave you f of x equals this, and we found the inverse was that. Now, something really cool happens when we do composition with inverses. If I do f of f inverse of x, so if I plug this one actually into this one, it becomes 2 times this stuff, x plus 6 over 2. What happens to the 2's? They cancel. What happens to the 6's? They cancel. And I'm left with x. Now, yesterday we did these, where we did plugged one into the other and then reversed it. We never got the same thing. But we're about to. Okay? This time let's go the other direction. Let's take this and plug it in there. So instead of x plus 6 over 2, we have 2x minus 6. We're plugging this in for x. Okay? Do you see the 6's cancel? And the 2's cancel? And I'm left with x. This is a special case. It only happens when the two functions you're given are inverses. If you do composition both ways, and both times you get x, then you have proven that the functions are inverses. And you have to do it both ways.
Just do like the complementary of the composition.
So,
Is that what you would call the opposite of
I don't know what we call that. You have to do the composition both ways.
it? Okay.
So you plug one function in and then the other function in. And if both times you get x, then they are inverses. Now there's special cases where when you plug them in both ways, you don't get x. But for us, we're somewhat limited. And with the functions we're studying, if you get x one time, you should get it the second time. So use that as a check step. Make sure you show it, but use it as a check step. But you're going to notice, if you get x one way, for the functions that we're studying, you will generally get x the other way. Okay? And now we have class time. A lot of class time. 25 minutes, which is enough class time for me to assign you more problems than I have, but I'm not going to. I'm just going to ask you to do these. Okay, so I'm going to quit recording now, and you're going to have the opportunity to get a book if you would like one of the new advanced algebra books. And then I'm going to come by and record those numbers. Now, once again, you don't have to because you can get the stuff offline.